An engine is basically a controlled explosion machine, which sounds unsafe, and historically it was. But somehow, engineers figured out how to make explosions happen thousands of times per minute, inside a metal box, right in front of our legs, without killing us. So today, let's talk about why engines explode, why that's actually the goal, and how engineers convinced explosions to behave. Defining the explosion. First, we need to clear something up. Engines don't explode like a grenade. They don't detonate. What they do is combust. Combustion is just rapid burning, fast enough to create pressure, but slow enough to stay controlled. Think of it like lighting a match versus setting off fireworks in your kitchen. Both involve fire. Only one ends with you calling your insurance company. In engineering terms, this difference matters a lot because pressure you can control is useful, and pressure you can't control is very expensive. An internal combustion engine does exactly one job. It converts heat into motion. You mix air and fuel, you compress it, you ignite it, the gases expand, and that expansion pushes on a piston. That piston is connected to a crankshaft, and the crankshaft turns linear motion into rotation. No magic, no mystery, just thermodynamics doing unpaid labor. The entire engine exists to repeat this process as reliably as possible for millions of cycles. Four-stroke cycle. Most cars use what's called a four-stroke cycle. 4 distinct steps, one controlled combustion event per cycle. Let's break it down. First, intake. The intake valve opens and the piston moves downward, pulling in a mixture of air and fuel. Second, compression. The valve closes, the piston moves back up, and the air-fuel mix gets squeezed. Smaller volume means higher pressure, and higher pressure means higher temperature. Third, power. The spark plug ignites the mixture. Not an explosion, controlled combustion. The burning gases expand rapidly and force the piston downward. This is the only stroke that actually produces power. Fourth, exhaust. The exhaust valve opens, the piston comes back up, and the burnt gases are pushed out. Then, the cycle repeats. About 2,000 times per minute at idle. Several thousand more if you enjoy accelerating. So yes, your car runs on fire. Just responsibly. If you wanted to draw what's happening inside the cylinder, engineers use something called a pressure-volume diagram, or PV diagram. On this graph, volume is on the horizontal axis, pressure is on the vertical axis, and one full loop represents one complete four-stroke cycle. As the piston moves down during intake, volume increases while pressure stays low. During compression, volume decreases and pressure rises sharply. The combustion event shows up as a sudden jump in pressure at nearly constant volume. Then, during the power stroke, the expanding gases push the piston down, doing useful work. That's the area inside the loop. That enclosed area is literally the engine's work output. Finally, during the exhaust phase, the piston is pushed upwards again to get rid of the exhaust gases, and the cycle begins again. Two-stroke cycle. Now let's talk about two-stroke engines. These are the engines that looked at efficiency rules and said, "Interesting suggestion," ignored. Instead of separating everything into 4 steps, two-stroke engines overlap them. Intake and exhaust happen at the same time. Compression and combustion happen every rotation. That means more power for the same engine size, fewer moving parts, and a much simpler design. It also means worse fuel efficiency, higher emissions, and significantly more noise. That's why two-stroke engines are common in chainsaws, dirt bikes, and leaf blowers. They're light, powerful, and absolutely not subtle. The two-stroke PV diagram looks similar to the 4 strokes at first glance, but the shape tells a very different story. Instead of a fancier-looking loop, you get a more compressed, aggressive cycle. There's no dedicated intake or exhaust stroke. Those happen while the piston is already moving. Pressure drops and rises more abruptly. Combustion happens more frequently, and the loop is tighter. This means more power events per revolution, but less time for efficient gas exchange. In other words, two-strokes trade refinement and efficiency for raw power and simplicity, and the PV diagram shows that trade-off visually. Gasoline versus diesel. Now, gasoline and diesel engines both rely on combustion, but they disagree on how combustion should start. Gasoline engines use spark ignition. The air-fuel mix enters the cylinder, gets compressed, and a spark plug provides the ignition source. It's simple, predictable, and easy to control. Diesel engines work differently. They compress air so much that it becomes extremely hot. When fuel is injected, it ignites automatically. This is called compression ignition. Because diesel engines rely on pressure instead of sparks, they operate at much higher compression ratios. That leads to higher efficiency, more torque, stronger internal components, and louder, heavier engines. Which is why diesel engines live in trucks, ships, and machines that are expected to suffer for decades. The physics involved. Gasoline engines use sparks. Diesel engines weaponize pressure. From a physics standpoint, engine combustion is called deflagration, not detonation. That means the flame front moves slower than the speed of sound. The fuel doesn't all ignite at once. The burn spreads gradually, like a wave moving through the cylinder. The burn spreads through the mixture as heat ignites nearby fuel, not as a pressure shockwave. Diffusion helps fuel and air mix, but deflagration describes how the flame itself actually travels. Diffusion decides where combustion can happen. Deflagration decides how it happens. If combustion happens too fast, you get detonation, and detonation is bad. That's what engineers call engine knock. Uncontrolled combustion happening at the wrong time and in the wrong place. Knock creates shock waves, damages pistons, destroys bearings, and converts money into sadness. So when we say engines explode, what we really mean is this. They perform tons of controlled combustions, precisely timed, carefully contained, and optimized for efficiency. Modern engines are not violent machines. They're disciplined systems. Every valve opening, every piston movement, and every ignition event is calculated down to milliseconds. Engineering is just the process of turning dangerous physics into useful work. An engine isn't chaos. It's fire on a schedule. So the next time you hear an engine rev, remember, that sound is thousands of tiny combustions working together so you don't have to walk or bike with your groceries from the supermarket.